Good afternoon. Really nice to see a turnout here. It gives me great pleasure to welcome you to the Excellent Series. The series celebrates the outstanding work of our leading researchers, highlights the meaningful impact of their contributions, especially the impact that they have at both national and international levels. I think through these talks, we aim to spark important conversations, showcase innovation in our land-based sectors, and demonstrate the vital role academic research plays in addressing real-world issues, especially given the flavor of the current government, the desire for us to make real impact. Today, I'm delighted to welcome Associate Professor Peter Almond. Peter is a distinguished soil scientist, as most of you know. His research bridges soil science and the broader earth sciences. His expertise spans earth surface processes, biogeochemistry, natural hazards, and paleoclimate. Central to his work is the idea that soils are dynamic, temporary features of the earth's surface, integrating the effects of natural processes and recording traces of past environments within their properties and layers. With a unique perspective that draws on geology, geomorphology, geochronology, and climatology, Peter's research has led to important breakthroughs, from redefining the rates at which rock weathers into soil to advancing our understanding of CO2 fluxes in Antarctic soils. These discoveries are crucial for improving how we understand Earth system responses and feedbacks in the face of climate change. This afternoon, Peter will explore what geological record can tell us about past analogues to today's climate crisis and the mechanisms and timescales of Earth's recovery. He'll also discover the emerging technology of enhanced rock weathering and how it could be applied in agricultural systems here in Aotearoa, New Zealand, contributing to Lincoln University's own climate goals. Please join me in warmly welcoming Associate Professor Peter Almond.
Kia ora koutou. Thank you very much for attending this talk. The turnout is good. I'm gratified. I am a soil scientist, a particular kind of soil scientist, a pedologist. So I deal with how soils form, the properties that emerge from soil formation, the spatial distribution of different kinds of soils, and how they interact with ecosystems, both agricultural ecosystems and natural ecosystems. And following the convention, following the convention Chad set up, I think last time, was old photographs of ourselves. This one of me, I'm there on the right, and that right-hand one, and the others, is 40 years old. I think Chad's wasn't quite that. But I started my career in pedology working in the forests of South Westland, on the west coast of the South Island. And I worked for the Soil Bureau, New Zealand Soil Bureau, and the Forest Service. And I had various tasks, but one of them was to try and understand the influence of soils on the forests, so to better understand how they might be managed, because that was a consideration back in those days about managing these forests rather than having them purely in the conservation estate. This is one of the forests I worked in. It's called saltwater forest. And what I quickly learned about that area was that its landforms were strongly influenced by climate history. The landforms were generated or constructed by glaciers, and I've tried to reconstruct what the most recent iteration of the glaciers were in this landscape. But you can probably appreciate the whole of the landscape was constructed in this way. And the timing of those glacial advances set up the pattern of landforms and the patterns of soils. And that pattern of soils transferred into the structure and composition of the forest. And it was with those ideas that we attempted to manage these forests in perpetuity. That's all finished, but that's where I started. And so I spent a lot of time thinking about climate history, the most recent, recent climate history, the last 100,000 years or so. So I was dealing with this kind of conceptual flow diagram. thinking about how climate influence landforms and how landforms influence soils, and from there, how soils influence ecosystems. But I've more recently started thinking more about this, which is what a lot of my colleagues do, how soils influence climate. And obviously the link between the two is greenhouse gas exchange. Some of our colleagues that work on nitrous oxide, methane, carbon dioxide and organic matter. And I'm focusing on carbon dioxide as well, but in a slightly different way. My first foray into this area of research was collaborating with a scientist now at the University of Massachusetts, Isaac Larson, and a colleague, Andre Egger. He isn't here today, but he works for, Landcare, Manaki Whenua. And we were asking some big global scale questions of, can the uplift of mountains and the enhanced chemical weathering that generates in soils actually control Earth's climate at long time scales, big spatial scale, well, global scale, obviously, global climate. And this was my introduction to the idea of the interaction between soils, weathering, carbon dioxide, and climate. So I'm going to go back a little further now. I'll go back 4 billion years or so. And note that our sun sits in about here now, our star's evolutionary sequence. It's called a main sequence star. And over its lifetime, last 4 billion years or so, it's got bigger and it's got brighter. So going back 4 billion years, close to the origin of life, a little bit further back, we had about 0.7, 70% of the solar luminosity we have now. And if you go through the physics calculations, we should be about minus 50 degrees Celsius. And obviously, that's below, water's frozen. Life probably wouldn't have kick-started. So from the time of the earliest formation of our planet through to the present day, despite an increasing luminosity of the sun, our planet has remained habitable. And the only way you could do that is if back in the origins of our planet, we had much higher greenhouse gases in the atmosphere. Something like potentially 10,000 ppm. And now you'll all know what we are currently, around about 400, 420 ppm. So what happened to all the greenhouse gases? What's provided the thermostat to keep our planet so modulated climatically, so habitable? And the answer is silicate weathering. So I guess the theme of my talk is, can we hack that process to try and get us out of the current of the rain? So what's involved in silicate weathering? Here's a silicate mineral. Minerals you find in rocks. Here's some pictures of them under a microscope. Carbon dioxide reacts with water to form a weak acid, carbonic acid. It's the stuff that's helping to dissolve up parts of the library in Ivy Hall. Go and have a look at it. And as a result, we end up with, after the weathering process where the silicate mineral reacts with that acid, an acid-base reaction, we end up with dissolved CO2 in the form of bicarbonate. And we have these things, these positive charged ions we call cations. So when you hear me talk about cations, we're talking about positively charged ions and some other things that form. So that's essentially the engine house of silicate weathering when it comes to sequestering CO2. Carbon dioxide in a gaseous form in the atmosphere dissolves in water. It reacts with minerals and becomes a stable, soluble form in water. And that bicarbonate and the cations end up in the ocean, and they end up there for a long time, at least 100,000 years, the residence time of the bicarbonate. So we can look to this for a long-term storage of carbon dioxide that far outweighs something like, for example, growing pine trees, which we might hopefully have time to return to. So here's the overall picture. We get weathering on land, carbon dioxide reacting with water, releasing cations, which end up in the ocean with bicarbonate. And the cations in the ocean, ultimately, they reside there for long periods, and the positive charge of the cations helps to support what we call carbonate alkalinity. Carbon dioxide dissolved in the forms of bicarbonate and carbonate. Over the long term, that bicarbonate and carbonate is incorporated in the biogeochemical cycle of formation of solid calcium carbonate, making up tests of microflora and fauna in the ocean, and skeletons and shells and so on. They end up in the ocean floor, they form limestone, and ultimately they're cycled by plate tectonics and our rock cycle, and they end up back in the atmosphere through metamorphic and volcanic processes. That's the big long-term inorganic carbon cycle. And it does act as a thermostat. When we've got high CO2 or hothouse world, so this process hasn't only modulated our climate over 4 billion years, it's helped us recover from perturbations. So high CO2 hothouse worlds like the Paleocene Eocene thermal maximum 50 million years ago, 10,000 ppm again. 1,000 ppm. High CO2 fires up the hydrological cycle, warm and wet, that fires up weathering, decreases CO2 and acts as a negative feedback. Likewise, we've been in icehouse worlds in the past, and in those conditions, low CO2, cold planet, weathering is slowed down, and volcanic emissions continue, and CO2 rises in the atmosphere, and there's the feedback, and that warms it up again. Wonderful. But it's a little slow. By the way, some of the best slides here, you'll see them acknowledged. Beulah Pragg, a 311 student of mine who presented the other day on this, and did a beautiful job, far better than I could do. So she'd given me permission to steal his slides. So if we look at simulations of how this process might help us recover from what this perturbation we're heading for, probably, or maybe 1,000 ppm with what we're doing, we're talking about 1 million years recovery time. It's a bit slow. But we can speed up this weathering by using reactive rocks. That means ones with reactive minerals, finely ground to make them high surface area and hence chemically reactive, and put them on agricultural lands in the most acidic part of soils, the upper horizon, and generate, hopefully, this flux of cations into the ocean that sucks CO2 out of the atmosphere, reduces ocean alkalinity, and reduces the atmospheric concentration of CO2. So it has a great potential in agricultural ecosystems, and what's more, it doesn't compromise agricultural production. It can happen alongside agricultural production. So what are the potentials for this? There's been a number of modelling studies using, say, focusing on the tropics, warm, wet, acidic soils, starved of reactive minerals because long time periods of weathering, and estimates of 88 gigatons CO2 per year. Current fossil fuel emissions, around about 40 gigatons per year. So that's enormous. That's a little optimistic. Analysis of UK croplands, 6 to 30, note the change of units here, megatons per year. Global croplands, 1/2 to 2 gigatons per year, at a cost of maybe 50 to 200 US dollars is the meta-analysis of all of this. So it's not insignificant. It's not, and I don't believe this tropics on, but it's not going to get us out of the mess we're in. We have to stop putting CO2 into the atmosphere at the rate we're doing. There's no way around that. But we could buy ourselves some time with this technology. It has upsides along with sequestering CO2. It has a liming effect. It neutralizes soils because cations in the rock end up on, but as cations on the exchange sites and in soils, and that's what neutralizes soils. It provides, depending on what rock you're using, it provides nutrients like phosphorus, potassium, calcium, obviously. It has been shown to enhance carbon, organic carbon accumulation, I should say. It's also been shown to decrease organic carbon accumulation. I've got a student sitting in the audience here, Mila, who's working on a question related to that at the moment. Improved aquatic health. As rocks dissolve, there's a flux of silica into streams in the dissolution process, and that silica can shift ecosystems into one dominated by diatomaceous creatures, algae, that can help with problems of eutrophication of waters. Reduce ocean acidification, as I talked about earlier, and there's some evidence that shows that it reduces other greenhouse gases like nitrous oxide as well. And that's mostly through the effect of pH, I understand. Some of the downsides, some of these rocks, depending on what you use, have heavy metals in them. So you could end up with concentrations of heavy metals in the soil. That rock that's favoured, any of you know about Dung Mountain and Dungite? Ultramafic rock is called. Very high calcium, very high magnesium, very potent when it comes to sucking CO2 out of the atmosphere, but very high in chromium and nickel. Basalt is another favourable rock. We'll come to that. Lower concentrations, but still a lot of rock additions potentially problematic. Dust risk. See a photo of this shortly. Decreased organic carbon, as I said before. Mining. Clearly, New Zealand has not much, what's the word I'm looking for? Does not favour mining. It hasn't an appetite, that's the word I was looking for, mining. So if we were to go whole-scale mining of mafic rocks for this, look out. But, you know, what we're going to have to consider the worst of perhaps two bad scenarios. And alterations to river chemistry, I've said that it can be a positive, it can be a negative as well. You flush a lot of basins into rivers from the weathering on land, and the pH of water can rise. You can even get carbonate precipitating in waters, which generally isn't good for inland waters. So one thing, if we're going to use this technology, is we need to quantify its effectiveness. There's a lot of in-field measurements, a lot of different techniques used to do this, but my colleagues and I, Stefan Hoibeck of a consultancy, BPO, and Andre Egger from Manaki Whenua, were contracted by MPI to come up with a way of quantifying enhanced rock weathering sequestration of CO2 that might fit into the New Zealand greenhouse gas inventory. Why is that important? Well, it's the way we measure our greenhouse gas emissions. We quantify whether we're meeting our nationally determined commitments under the Paris Accord. Climate Change Commission uses it for their analyses. And ultimately, it may lay the grounds for carbon credits under the ETS if, for example, agriculture was ever brought into the scheme. So we adopted what most of our greenhouse gas inventory method comes up with. That is a tier 1 or tier 2 method. It's sort of a hybrid. Pretty simple. You say the amount of, and the current greenhouse gas inventory deals with emissions. It says the emissions are related to how much of an activity you're doing times its emission factor, its intensity of emissions. So we adopted the same framework we were told to. So here's an example using liming. Lime emissions in New Zealand is how much lime you apply times the emission factor, how much CO2 is released by adding a ton of lime to the soil. The activity data is easy. Where the quarry surveys, there's fertiliser companies, we can easily quantify how much basalt we grind up and add to soil. So let's just move on. The hard part is what's the emission, in fact, what's the sequestration as you add basalt to soil. That's what we really had to think about. And we started off trying to come up with this sequestration factor, and obviously it depends on the chemistry of the rock. If you add that stuff we've got in our backyard, gravity, for example, that's dominated by quartz and feldspars, that are sodium dominated, you don't get much effect. You add basalt or dunite, you're going to get a strong effect. That effect is quantified by something we call RCO2, and I'll show you roughly what that means. Any speed limitations, it's fine saying this rock will weather, but will it weather in a reasonable time frame that it makes a difference? So those are what we call kinetic effects. You remember the engine house of all of this is the cations. How much cation is released and where does it end up? If the cations that are released by weathering end up in grass or in sheep or in us and not in the ocean, then you don't get an effect. And finally, is it actually carbonic acid that's doing the weathering? It might be some other acid. So we built in these three factors. Okay, so sorry. So the alternate acid effect, as we call it, if you've got a lot of nitrate around, as we do in our agricultural systems, you can end up with nitric acid doing the weathering. And just note from the chemistry, the bicarbonate's not there any longer. Likewise, if you've got a lot of sulfate around. So here, this complicated formula, don't worry about it. This is the RCO2. This is essentially how potent the rock is. It's essentially just sum up the amount of effective cations in the rock and equate it to how much CO2 that represents. There's one other correction, and this is omega number here, and that's, does the stuff end up as monovalent carbonate or divalent bicarbonate? And that determines how many CO2 molecules you store. But essentially simple. It's an accountancy exercise, how many cations per unit mass in the rock. And if we look at a common rock that's around New Zealand, like basalt, you'll see it sits here in this classification of igneous rocks. It has an RCO2 of about 0.3. What does that mean? You put a ton of it on, and in theory, 300 kilograms of CO2 will be sequestered. But remember, there's other effects that might be discounted. So the kinetic effects, going through them one by one, the speed limits. Modelling studies, because we haven't got long-term field trials, modelling studies suggest 30 years, finely ground basalt, you could expect 80% of effectiveness of weathering. So there's our kinetic limitation we use in our formula, 0.8. Cation retention. We don't think it's a big problem because we decided to use an accounting period of 30 years for our method, just similar to what forestry uses, a 30-year accounting period. I suspect that if you eat some cations coming from the rock weathering, they're going to end up in the ocean before 30 years. I know how much effluent we make. You know, it goes through us and ends up in, all our effluent pretty much ends up in the ocean. So I think that's not a big problem. And this alternate acid effect, well, it's hard to quantify. It's going to vary depending on different agricultural ecosystems, but we think we've got a way of dealing with it. So in the end, we came up with this. CDR, carbon dioxide removal, equals the kinetic effect, 0.8, times the cation retention effect. We don't think only 5% cation retained, times this alternate acid effect, which I won't go into, it's complicated, another 0.8. And when you multiply those are multiplied by this RCO2 thing, the potency of the rock. So we came up with this, which MTI really liked, because it's simple. 0.61 times RCO2. Looking for feedback on that, by the way. So in the case of if you use a basalt, we could expect now with this discounting from a ton of basalt, 180 kilos over a 30-year period. Cool. So basalt, how much of it? Here's an analysis. This is Andre's work. Analysis of basalt New Zealand is pretty widely spread. The diagram on the left is all basalt we grade out the area that's under conservation land, and still there's reasonable distribution of basalt throughout New Zealand relative to the agricultural areas we've got. So if we think about what could this technology do for us, let's start really simply and say, instead of liming, because you know adding rock has a liming effect, let's use basalt instead. We think we need about a 5 to 1. There's a lot of we think, because that's who we're going to be done. We think it's about a 5 to 1 ratio probably necessary. So New Zealand applies about 1.2 million tonnes of lime, which is about, according to the greenhouse gas inventory, worth about 0.5 million tonnes of CO2, which is part of our emissions. If we say we replace that with basalt, with this 5 times multiplier, and there are some data to help support this, we need 6 million tonnes of basalt applied per year. According to our formula, that would get us about 1.1 million tonnes of CO2. If we add also that we're not emitting 500,000 tonnes of CO2 from lime, we've got effectively 1.6 million tonnes combined reduction. That's about 4% of New Zealand's agricultural greenhouse gases. That's just replacing lime. That's not insignificant. So what would it cost? Assume 5 tonnes of basalt per tonne of lime. So we've got 5 tonnes times roughly $70 spread. Subtract the cost of, you don't have to add a tonne of lime. So if we're doing 1 tonne of lime per hectare, so we got 4 times 70 or $280. The CO2 removal using the formula, 5 times 0.18, remember that number. And so you end up with 0.9 tonnes of CO2. We avoid emitting 0.4 tonnes of CO2 from the lime we didn't add. We end up with 1.3 tonnes of CO2. $280 will get us 1.3 tonnes or $215 per tonne of CO2. Expensive? Cheap? Here's New Zealand's current situation. We're short for our 2030 targets of 80 million tonnes of CO2 roughly, depending on where we get our carbon credits from. That's going to cost us somewhere between $3 billion and $23 billion. We're likely, the Treasury says, to be ending up buying our credits from the likes of Switzerland because we've delayed so long. And we could be paying close to 250, these are New Zealand dollar per tonne. So we sit in here with enhanced rock weathering, potentially, but we're spending the money here, we're not spending it in Switzerland. And you might have noted Winston Peters' aversion to spending any money outside of New Zealand. So that could pay. Lincoln University, we have a target of reaching 2,500 tonnes CO2 by 2030. And this is how we've been tracking. We're going to get a big reduction in 2025 with that coal boiler not spewing out coal gas anymore. But we've got a ways to go to get to this 2,500 tonnes. So if we did this on our own farms, where we added equivalent of a tonne, 5 tonnes per hectare, replacing a tonne per hectare of lime on our local farms, we can do something like this. Not insignificant. So it may be a technology that Lincoln University wants to support in the way of research initially, but heading to the aim of having this accounted for as a carbon dioxide removal, and hence contributing to our carbon neutral 2030 status. But we've got to validate all of this. And so there's some research going alongside the greenhouse gas inventory work. And this is unfortunately down in Southland. It's hard working in Southland. But we had a previous PhD study there. Landcare, collaborated with Landcare. We set up a catchment study for another purpose, but it was instrumented really nicely with a whole lot of kit worth about $500,000 in the end. So we're exploiting that. And the kit looks like this. We've got soil moisture sensing. We've got met station. This landscape, by the way, is mold and tile drain. So it's like a huge lysimeter. We can catch all the water that drains from it. Well, not quite all the water, most of the water, because the central tile drain runs out of the catchment. We can catch overland flow. We can, with this amazing looking device here, it's not a Segway. It's a tile flow monitoring meter. And we've got an auto sampler, thing that goes into the tile, sucks water out, so we can get the chemistry of the water, we can get the flow of the water, and by multiplying the two together, we can get the flux of cations coming out of this landscape. And by that, we can estimate the CO2 removed. So in March, we did this. 50 tonnes per hectare, not 5, 50 tonnes per hectare of basalt supplied from a collaborator in Dunedin, Blackhead Quarry. 2 bulkies operating simultaneously for 7 hours, got 50 tonnes per hectare on 5 hectares, so 250 tonnes applied in one day. They're amazing operators. Dust. You'll see the dust. A liability. That's the operation. This is what it looked like the day after. Someone said 50 tonnes per hectare, you'll be able to build a house foundation on that. It's not that grand. There it is a day after. You'll see the dark coloured basalt in amongst the grass and some of it creeping down to the soil interface already. And Mila and I went back a month later, and early in the morning, the red glow of dawn with the frost still on the grass. You'll see now all the basalt's made its way down to the soil interface, which is nice. And here is what those wonderful operators did. Here's a drone. We took our new drone down there. The however many $1,000 drone, $75,000 drone. And we took photographs. And this outline is not a real outline on the ground. This is in GIS. I've overlaid the catchment boundary on what those guys did with their bulkies. I gave them the catchment boundary. They had it in their GPS system, and that's how good they are. Excellent. And so now we wait. This is rainfall from about November last year. These are the rainfall events, and these little black spikes. This blue is the cumulative rainfall, and that's the ET, evapotranspiration. This is tile flow, and you can see the thing shut down in December. It got dry. We're waiting with bated breath to see what flushes out. We need more validation, and some of you may recognise this. I know Linda will do at the back of the room, and she's coached me on this so many times. This is Lincoln University Research Dairy Farm. There's a plantain trial on there currently, and in the plantain, which Linda is managing, the paddocks have porous plugs. You can suck soil solution out. They have lysimeters for measuring drainage. We can do the same thing on the Lincoln University Dairy Farm if we're given access to it. And we don't necessarily have to impinge too much on existing trials. So this is where Lincoln University can contribute. And I'll leave you with a couple of slides, depending on where we are headed. These are the shared socio-economic pathways. This is probably what we do if we're good boys and girls. This is if we're not. High CO2 emissions for long periods. The yellow is what we're going to need to suck out of the atmosphere. And currently the expectation is we're going to do that by bioenergy with carbon capture and control. Growing crops to burn and then suck the CO2 out of the atmosphere. That's expensive. And it compromises agricultural production. I don't think it's a goer. This is what the present government's thinking about, 280,000 hectares of pines on public land. Oh, that's terrible colour coming out. I'll read. Simon Upton says, the world actually needs real reduction in gross emissions, not an accounting triumph. Daniel Melia from Victoria University Climate Research Centre says, I foresee that carbon forestry will become what mortgage-backed securities were to the global financial crisis. Pine trees are not the answer. Enhanced rock weathering is not the answer. It's part of the answer. We know what the real answer is. Change our lifestyle. That's me.
Peter, fantastic talk. Really enjoyed that. I'm sure you have plenty of time to answer questions, but I do appreciate the brevity and specifically translating what is a very complex problem into layman's speak. So thank you.
Yes. Peter, you didn't mention the energy or effectively carbon cost of mining, grinding and spreading 50 tonnes per hectare of rock.
Yeah. Thanks, Alistair. I knew that question would come up. There's two answers to the question. One, when it comes to the greenhouse gas inventory, they occur in other sectors. So as far as agriculture is concerned, we can forget about it. That's a trite and unsatisfying answer. There has been analyses done on the grinding costs, and obviously the CO2 cost depends on whether you use fossil fuels or electricity to grind. So I could show you those figures. It's not too big a penalty. Our man down in Blackhead Quarry says it costs him, and he uses electricity for his main grinder and then a sort of portable, smaller one, fossil fuel, diesel powered. He says it's costing him 1.6 kilograms of CO2 per tonne of ground rock. So compared to the maybe 180, it's not a big penalty. Now that doesn't build in, transport or the mining costs. But again, it does depend a lot on, the energy source you use for those things. But it still works, and these global analyses have included all that life cycle analysis. We need to do it in New Zealand.
Interesting that a whole bunch of work was commissioned by MPI. What level of traction is there in government, both bureaucracy and at the political level, on this now?
Well, I can tell you that there's a greenhouse gas symposium coming up in May, this month, late May, early next month actually. And I offered a talk on this, and they said no, it's not. They want to talk about methane inhibitors.
Yeah.
They still want to bang on about a methane inhibitor. My Chad's controlling.
No, you can control it. Just on there, there's the list of greenhouse gas mitigation options. As far as I'm aware, there's one only. This here at the University of Ecopon. All the others are years away. So I'm not quite sure why they should be so dismissive on methane inhibitors, because I think there's going to be a long time before any of those are going to be having much effect on reducing methane by the time they get through a whole lot of trials and issues to be contended with. But just getting back to your back to the silicate minerals, what are the health implications? I mean, grinding silicate minerals to a very fine powder. You know, we've already had stories in the media around silicosis and you know, people's, you know, being damaged by, you know, with dealing with silicate minerals. You wouldn't need too many cases for it to kind of, you know, people would start to not support it. So, like, what are the health implications around grinding silicate minerals?
Well, the health implications are dire, obviously, if you suck the stuff in. So it then comes down to how you treat the material as you're grinding it, and in fact, how small you have to grind it, and that's an active area of research. I reviewed a master's thesis last year that used as an analogue for this basaltic volcanic ashes from New Zealand, and showed that the Tarawera locally, 1886, you know, so we've got 140 years of weathering on that. It didn't have to be particularly fine because there are a whole lot of surfaces within the grains that we don't account for between the minerals, and they turn to be active pathways for weathering. So maybe we don't need to go super fine.
You mentioned effects like heavy metal contamination and also river chemistry being affected, and you also mentioned pH in the soil. Is there any other awareness about the soil chemistry that is affected by this treatment?
Soil chemistry. Well, we know it influences soil microbes. We know it has some effect, contradictory, has some effect on the partitioning of different forms of organic matter between labile and recalcitrant forms. Say they're contradictory. There's a whole lot. I saw a recent paper on the effect on the expression of genes, and it definitely has an effect on the expression of genes. But you only have to look. Fertilizer does the same thing. It's not that it's going to have any effect that I wouldn't expect fertilizer to have, that we're currently pretty comfortable. Use Mr. Lutson's words. Comfortable with him. Comfortable with him. I'm comfortable with it.
Yeah. I remember reading a while ago project where they were talking about dumping olivine rock on rough beaches and using the theory is they use the action of the tide and waves to sort of smash these little grains together and enhance weathering over time. Yep. So the waves do a bit of the work for you. Yeah. If you're aware of that, can you compare that to this approach where you grind it up finely?
Yeah, there's an ocean application of minerals as well. Yeah, on beaches, even directly dumping finely ground rock into the ocean. And yes, it will react. I'm going from the gut here that I think the chemical reactivity relying on elevated carbon dioxide in the soil to weather the rock material, that effect would be much stronger than the physical low CO2 environment of a beach. So, you know, CO2 in the soil, I got the numbers from our study site the other day. In the soil, we're talking, 15,000 ppm CO2. It's a lot of CO2. And so you get high concentrations of carbonic acid in the soils and other acids as well. So I can't give you a definitive answer, but my guess is soils would be more effective than beaches. Yeah.
What were the factors that led to your Southland trial site, other than perhaps the instrumentation at the site and the proximity to a source of basalt? And are there other likely candidates perhaps around the country?
Oh, yeah, there are other likely candidates. What led to it? Nothing more than what you've already said. That it was there, and the infrastructure was there. We had a cooperative farmer, more than cooperative, enthusiastic farmer. And when you go and apply 250 tonnes of basalt to his paddocks, You know, we've got to have someone who's on board. And he was, and we're looking at 5-10 years, hopefully, of this getting kit working. And so he's talking about that time frame. It's hard to get. Yeah, the dairy farm would work. Lincoln University dairy farm would work really nicely. If we don't have, if it's not cultivated and all the tubing to the forest plugs ripped up, because that's the prospect. Where else? Massey University in their nitrate trials have leaching setups where they use tile drains as well. There's other techniques. You can just look at what happens to the basalt in the soil to see how it changes from when you put it on to 2 years down the track or 5 years, and do an accounting and say, where are the cations? Assume you've lost them, assume they're in the ocean, and come up with a number.
Yeah, I'll play devil's advocate here. So soil pH is important in terms of weathering. What information do you know about in current modelling in terms of the rate of weathering and the pH of the soil that you're applying the rock to?
There was a study came out, I think it's this year or late last year, in the US in a soy maize system, applying 50 tonnes per hectare per year. The gains, the productivity gains are quite large. The addition of the nutrient inputs were large on using a nutrient budgeting approach, and the pH continued to rise by about half a pH unit per year. So you're thinking about the feedback between the pH rise and the weathering.
Yeah, I mean, for the initial pH of the soil you're applying, yeah. I mean, was that an alkaline soil, do you know, or was it an acid soil?
It was pH high fives, right? So similar to New Zealand sort of situation. The difference being, and I should have said this, nearly all the research has been in arable lands. You take the stuff and you mix it in with cultivation. What we're talking about here in New Zealand, if you're going to use it, you're going to add it to the top of pasture. That's probably going to be there for 5-10 years. So it's mixing. It's not going to be so effective. So we can't assume that we're going to get the same sort of results you get in arable systems elsewhere. So that's why we've got to do the empirical studies.
CO2 has to pass out of the soil. Generally goes up. So it's going to pass through that layer, isn't it?
Yeah, relatively low concentration, but you need water for weathering to occur. So the weathering has to occur in the soil with the grains of basalt in association with soil solution and with high dissolved CO2 in it, and not too much nitrate. The point with just too much nitrate, you know, what ends up leaching is not bicarbonate, it's nitrate. So one of the big risks is you add the stuff, you end up with a lot of cations, they get flushed, and all they do is carry nitrate with it and enhance nitrate leaching. That's what we need empirical studies as well.
Peter, there's a local company that grinds and granulates lime, sells fine lime. Great cost to farmers, and they spread it at a much lower rate, thinking that it's going to be as effective as 5 tonnes per hectare. It might be as effective over a short period of time, but probably not over a long period of time. But given that massive dust problem and potential health issues, is granulation, would that be feasible with this product?
Yeah, I'm out of my area of expertise, Elsa, I presume. So you mean making some permanent granule that dissolves up?
Yeah, it'll break.
Yeah,
as soon as
yeah. That addresses and Peter's or whose dust problem, Peter.
Yeah, and in terms of mixing in the soil, earthworm activities going to be really important in terms of actually, you know, moving and incorporating that material. They have a massive perturbation.
Yeah, well, there's plenty of earthworms in the paddock, and also we all know about Southland and pugging, and even with sheep, those paddocks pug in winter. So there'll be a certain amount of mixing with the pugging. So we'll track through time that mixing.
Of course, so long as it doesn't grind out the gut of the earthworms as they ingest it.
That's a basalt. One thing I will say, the guys who did that operation, they were very good. I was very impressed. But at the end of the day, he said, well, we effed our flails, mate.
Oh, yeah.
The flails that spread the rock from the track, an auger that takes it from the bin and the flails spread it out. They said there was half a season left in those flails till you came along. And the flails were wrecked for one day.
You have to take it.
They need to make them harder. Let's toughen up the flails.
One more question, and then
I think it has been just dominating the conversation.
I was just wondering, with the validation of how much carbon this is actually removing from the atmosphere. I mean, you're talking about kind of within paddock, within catchment measurements of what's coming out of the soil, kind of patterns and whatever.
Yeah.
Is that kind of the complete picture? Is there a concern that the alkalinity that's basically being transported out of those soils will be attenuated or stuck somewhere and won't actually draw down CO2? Or is that kind of like, if you manage to weather the rocks, you'll guaranteed get that amount of CO2 extraction? I guess I was just wondering if.
It's a really good question. If the alkalinity you generate ends up as solid calcium carbonate, then you end up with essentially discounting of your CO2 sequestration by a factor of 50%. Because if you have a divalent cation like calcium 2+, you can have 2 bicarbonates associated with it. As soon as it precipitates in the form of calcium carbonate, carbonate being divalent, you have 1 CO2 molecule per calcium. So we don't want carbonate precipitation. But there's not much to suggest from the work we've done that the calcium saturation levels in our aquifers or our rivers are such that we'll be getting it. So it'll end up in the ocean, and then once it's in the ocean, it will do its thing. And, you know, it's very difficult to change the bulk chemistry of the ocean. So it's not the full story, but we feel confident if we can measure what comes out of the field, we've got a pretty good estimate of the CO2 that's sequestered.
thank you very much, Peter. It's a wonderful suite of questions. I'm sure that there's plenty more over drinks, but in the meantime, we want to thank you for a wonderful presentation and join me in thanking Peter once again.